Welcome to the deep dive. We take those complex research sources you send our way and, well, we boil them down to what really matters, the actionable stuff. Today, we're tackling probably the single most expensive and maybe least understood part of building modern large language models, that's reinforcement learning, or RL. Now, we all kind of know LLM training happens in two main stages, right? First, there's the big pre-training phase. That builds the model's, foundational knowledge. And for that, we actually have pretty good scaling laws, predictable. But then comes phase two, RL. And that's the magic bit, isn't it? It unlocks the really sophisticated reasoning, alignment, the agent-like abilities. But here's the kicker. The sources are showing these RL compute budgets are just massive and growing. We're seeing things like 100,000 H800 GPU hours just for the RL part of models like DeepSeek R10. It's staggering. The problem, though, unlike pre-training, figuring out how to scale RL has been, well, more art than science. Lots of expensive guesswork. We haven't had a solid predictive way to do it.
That's exactly right. I mean, the core issue has been everyone's kind of doing their own thing, running these isolated, custom, super expensive experiments, hoping their particular flavor of RL scales up. There just wasn't a reliable way to tell early on, if an algorithm was going to hit a high-performance ceiling eventually, or if it would just plateau after you sunk a fortune in compute. That uncertainty, it's really held things back. So this deep dive, we're focusing squarely on what looks like the first really large-scale systematic study trying to fix this. They used over 400,000 GPU hours for experiments. Their goal was pretty straightforward: define a scientific framework, something predictive for RL performance, and, crucially, build a stable, robust recipe, they call it ScaleRL, that actually behaves the way the predictions say it should.
And the amazing thing is, it seems like they actually did it. They built the scalar RL recipe, ran it up to a massive 100,000 GPU hours, and the final performance, it tracked almost perfectly with what their framework predicted much earlier, using way less compute. This feels like the moment RL training starts getting, well, scientifically rigorous. So, okay, let's unpack how they built this new science. We mentioned pre-training scaling laws, often power laws. You have more data, bigger model. Performance goes up predictably along that curve. But RL metrics are different, aren't they? Things like accuracy, pass rates. They have a ceiling. You can't get better than 100%. And the sources show that if you try to plot RL performance against the log of compute using those power laws, it just doesn't work well. Unstable, unreliable for predictions.
Exactly. Power laws just don't capture that saturation effect. So instead, these researchers found that a sigmoidal curve, an S-shaped curve, fits the data much, much better, more robustly. This S-curve, it shows you get fast gains early on, that a period of rapid growth, but then inevitably, it starts to flatten out as you approach some kind of ceiling. And what's really powerful about using this curve is that it gives us three clear, interpretable parameters, three numbers, basically, that define how scalable a particular RL method is. If you're out there developing LLMs, these three numbers, they pretty much define your RL success. Okay, so the first one, and you could argue it's the most critical, is parameter dollar. That's the asymptotic performance. Think of it as the absolute maximum performance ceiling your method can ever reach. Throw all the compute in the world at it, you won't get past $8.
Okay, so honors is the hard limit. Got it.
Then there's a baller dollar. That's the scaling exponent. This tells you how steep the curve is, essentially how efficiently you use your compute to climb towards that ceiling. A higher dollar means you get there faster, more bang for your GPU buck, so to speak.
Right, efficiency.
And the third one is CB, the midpoint. This is simply the amount of compute you need to spend to get halfway to your total potential performance gain, halfway up the S-curve.
That's incredibly clear. A, B, C, me, ceiling speed, halfway point. Okay. But hang on, this raises a question for me. If $8, the ceiling, is the ultimate goal, why wouldn't developers just laser focus on finding the absolute highest dollars? Even if it means the climb is slower, a lower dollars, you've got a massive budget, maybe you don't care as much about the initial speed.
That's precisely the tension, isn't it? You should prioritize $8 if you're aiming for the absolute state-of-the-art at extreme scale. But the problem was finding it without spending that extreme scale budget first. This predictive framework is the key. It lets you take results from a, let's say, relatively smaller run, maybe 8,000 GPU hours fit the S-curve, and then extrapolate to predict what your dollar is likely to be way out at 100,000 hours or even more. Before this, like you said, you basically had to run the whole costly experiment and just cross your fingers, hope it paid off. This framework, it's about managing risk, predicting that final ceiling before you potentially burn millions.
Okay, that makes total sense. It becomes a vital tool for deciding where to put your resources. So, armed with this predictability, the researchers ran their huge study, 400,000 GPU hours worth, and they surfaced three core insights that really change how we should think about RL scaling. The first big one, those RL performance ceilings. That parameter $8. They are not universal. Different recipes at different ceilings. This means really fundamental choices you make, like which loss function you use or what batch size. They don't just affect how fast you improve. They actually determine how high you can ultimately go. You can't just assume any decent RL algorithm can reach the same peak.
Exactly. That finding pretty much invalidates a common assumption that maybe all modern RL algorithms are fundamentally equivalent if you just scale them enough. Turns out, no. If your choice of, say, loss function imposes a lower inherent ceiling, Arguller, you're capped, no matter how much compute you throw at it later.
Wow, okay, that's huge. What was the second insight?
The second one really underscores why this predictive framework is so necessary. They call it embracing the bitter lesson. It turns out that methods which look really good, really efficient at smaller compute scales, maybe they have a high dollar shoot up the curve quickly early on, can actually end up being worse when you extrapolate them out to the massive compute regime. Why? Because they might hit a significantly lower ceiling, a lower dollars.
Ah, I see. So you could get fooled by early results. You pick the fast starter.
Exactly. You pick the hare, but it runs out of steam halfway, while the tortoise, the slower starter with the higher ceiling, eventually overtakes it.
If you stopped your experiments early, you might commit to scaling up an algorithm that looks fantastic initially, but it's doomed to stagnate later, forcing you to maybe halt a massive run or restart. What a nightmare.
It confirms that small-scale results can be dangerously misleading for predicting large-scale outcomes in RL.
Okay, bitter lesson learned. And the third principle.
The third one sort of challenges some common wisdom around stability fixes and tweaks people often use in RL. Things like certain ways of aggregating losses or using data curriculums or normalization techniques. Many people thought these were directly improving the potential performance, raising the ceiling $8. But the study found that many of these common interventions primarily just affect the compute efficiency, the dollar parameter. They help you climb the curve faster, sure, but they don't really shift that ultimate asymptotic ceiling $8 very much, if at all.
That's a really critical distinction. So some knobs speed up the climb, others actually raise the destination.
Precisely.
And knowing which is key. Which brings us to how they actually built ScaleRL. They needed components that ideally raised a dollar or at least significantly boosted efficiency dollar and stability. So let's dig into the actual building blocks of this stable, predictable recipe.
Okay, yeah. The first big architectural decision was about the setup. They used something called asynchronous pipeliner RL8. Now, most people doing RL are probably familiar with PPO, proximal policy optimization, often run in an off-policy way. Pipeline RL is different. It's an asynchronous setup. You have separate workers. Some are generators collecting data by running the model. Others are trainers using that data to update the model. They run concurrently.
Okay, asynchronous. And the A88, what's that signify?
The 8 is important. It refers to the number of steps of off-policiness. Basically, how old the data collected by the generators can be before the trainer uses it. By keeping this pipeline relatively tight, only 8 steps old, they maintained a closed feedback loop between the generators creating data and the trainers learning from it. And this setup substantially improved compute efficiency, the blotter parameter, compared to more classic, more off-policy PPO methods they tested. That tighter loop just keeps the training more stable and closer to the ideal on-policy scenario.
Makes sense. Faster feedback, better efficiency. Okay, moving to the core of the learning, the loss function. This sounds crucial, especially given that first insight about ceilings. They compared the common Dampio loss, that's direct alignment policy optimization, right, with some alternatives, CICO and GSPO, lots of acronyms. What's the key difference for someone listening?
Yeah, it gets dense quick. At a high level, DAPIO is often simpler, more like a gradient-based approach, sometimes derived from things like behavior cloning. CISPO, though, stands for Truncated Importance Sampling Policy Optimization. Importance sampling. Well, it's mathematically a bit more involved. But the gist is, it's a technique to statistically correct for the fact that you're training your current model using data that was generated by an older version of the model. It tries to reweight the data points appropriately.
Ah, okay, so it's trying to handle the data being slightly stale in this asynchronous setup.
Exactly. And this difference turned out to be massive. Both CISPO and GSPO significantly outperformed DPO in their tests. They achieved a much higher asymptotic pass rate, a higher ceiling dollar. They ended up choosing CISPO for the final ScaleRL recipe. Why? Because even though it's maybe theoretically more complex, in practice, it was much more robust. It showed this prolonged, almost linear reward increase for much longer, and crucially, it was way less sensitive to tweaking hyperparameters, like a clipping parameter called epsilon max. DPO-style losses can be really finicky with tuning.
And that robustness is gold when you're talking about those massive expensive runs. You don't want things breaking because a hyperparameter was slightly off. Okay, CISPO for robustness and a higher ceiling. Now, there's a finding here that seems almost backwards, given the push towards a lower precision compute, the numerical stability fix. They found that using FP32 precision, so single precision floating point, specifically for the LLM logics, right at the very output layer, dramatically improved the ceiling of dollars from like 0.52 to 0.61. Isn't everyone trying to use FP16 or BF16 everywhere for speed and memory savings? Why go back to FP32 here?
That's the fascinating part. It's
Well,
because of what RL is doing. In RL, especially with important sampling like in CISPO, you're often calculating the ratio or the difference between the probability assigned by your current policy and the probability assigned by the older policy that generated the data. This difference, this ratio, drives the learning signal, the policy gradient, and often, especially when the policies are close, this difference can be tiny. If that tiny crucial difference gets lost or mangled because of the lower precision of FP16 or the F16, even though those formats are fine for most other parts of the network, then your learning signal becomes noisy, or worse, just wrong. By switching back to FP32 just for calculating those final largets at the language model head, they preserve the fidelity of that critical signal. It's a really surgical fix. It prevents numerical mismatches between the generators and trainers and keeps the learning signal clean enough for the model to actually learn effectively and reach that higher asymptote.
that is a brilliant example of finding exactly where precision matters most. It's not about using FP32 everywhere, just in that critical spot. Okay, so we have the asynchronous setup, the robust CISPO loss, the FP32 fix. What else went into ScaleRL? You mentioned some data management tweaks.
Yeah, a couple of other pieces that primarily boosted efficiency and stability, helping the whole recipe work together reliably. One was prompt level loss aggregation. Instead of averaging losses across every single token, they first averaged the token losses within each prompt, each input sample, and then averaged those prompt level losses across the batch. This specific way of averaging yielded the highest ceiling error among the methods they tried.
Interesting. Subtleties in averaging matter.
They do. Another was zero variance filtering. They simply filtered out any training prompts where all the generated responses received the exact same reward score from their reward model.
Why filter those?
Because if all responses get the same score, that prompt contributes literally zero useful information to the policy gradient calculation. There's no signal about which response was better or worse. Keeping that zero gradient data in the batch just adds noise and computational overhead without any learning benefit. Filtering it out resulted in slightly cleaner training and a higher fitted asymptote dollar.
Okay, removing useless data helps. And the last piece.
No positive resampling. This is a data curriculum strategy. They basically track the historical pass rate for each prompt over time. If a prompt consistently achieved a very high pass rate, say 90% or more of the generations passed the criteria, they just permanently removed that prompt from the training data set for future epochs. The idea is to stop wasting compute on problems the model has already effectively mastered. Focus the learning on the harder stuff. This improved efficiency and also seemed to help scalability, contributing to a higher final reward and asymptote $8.
Got it. So looking at the whole package, pipeliner LO, ECISPO, FT32 logics, prompt level averaging, zero variance filtering, no positive resampling, it really feels like ScaleRL's success comes from systematically identifying and fixing all those little sources of instability and inefficiency they found during that massive 400,000 GPU hour exploration.
That's exactly it. ScaleRL isn't necessarily about one single magic bullet component. It's defined by its overall robustness. It's a collection of these, maybe individually small-looking design choices, but cumulatively, they address the recurring headaches, the variance, the sensitivity, the numerical issues that tend to plague RL when you try to scale it up massively.
Right. Okay, so let's switch gears slightly. Imagine you're listening, you've decided to adopt ScaleRL, and you have a fixed compute budget. Now you need to decide how to spend that budget. What are the most effective scaling knobs to turn with this recipe? Where do you get the most reliable bang for your buck in terms of performance gain?
Great question. The study looked closely at this, identifying three main scaling axes, where ScaleRL showed predictable, positive scaling, particularly for improving that crucial ceiling parameter, $8. First, and maybe not surprisingly, is model scale, just making the model bigger. They found that scaling up the model size substantially improves the asymptotic performance, $8. Their larger model, a 17B parameter mixture of experts model called Scout, achieved a much higher final RL performance ceiling than their Einstein 8B dense model. And get this, it did so using only about 1/6 of the total RL training compute. So bigger models weren't just better, they were potentially much more RL compute efficient in reaching a higher peak.
Wow, so bigger is definitely still better, even deep into the RL phase. That's a
Yeah,
strong signal.
absolutely. It directly lifts the ceiling.
Yeah.
The second reliable knob is generation length, which you can think of as the context budget during RL. They found that increasing the generation length, say training the model to handle interactions over 32,000 tokens instead of just 14,000, does tend to slow down the initial progress. Your ball of parameter might be lower.
Okay, so it takes longer to get
Right,
going.
and this is key training with that longer context consistently and reliably lifts the fitted asymptote dollars. It means that investing compute in longer context RL isn't just an efficiency trade-off. It actually unlocks a higher potential peak performance. If your goal is the absolute best final capability, you probably need to budget for longer context RL training.
That's fascinating. So it tolerates slower early gains for a higher ultimate ceiling. What's the third axis?
The third one is global batch size. Using larger batch sizes during training, they found larger batches reliably improve the asymptote dollars, and maybe just as importantly, large batches helped avoid performance stagnation they sometimes saw later in training runs that used smaller batches. This stability benefit was apparently crucial for why their big 100,000 GPU-hour run matched its predictions so well. The large batch size kept it stable all the way.
Okay, so bigger models, longer context, larger batches. Those seem to be the reliable ways to push ScaleRL performance higher, primarily by raising that ceiling A0. Now, something you touched on earlier, but I found really surprising in the findings, was about entropy. They tracked model entropy, which is sort of a measure of its uncertainty or randomness during training, and they saw it consistently go down in all runs, which you might expect as the model gets more confident. But here's the weird part. That decrease in entropy was not a reliable predictor of how well the model actually performed downstream, especially when comparing runs with different batch sizes. The large batch runs ended up performing much better, but their entropy curves looked almost identical to the worst performing small batch runs.
Yeah, that's a really critical counterintuitive point. It strongly reinforces the idea that you can't just rely on simple internal training metrics like entropy as a proxy for actual scaling success or final performance. If you'd only been watching the entropy, you might have incorrectly concluded that the small batch runs were doing just as well or were on the same trajectory. It really hammers home the need to focus on fitting that sigmoidal curve and tracking those macro parameters, $8 and buy dollars, to truly understand and forecast performance at extreme scale. Don't get fooled by misleading internal metrics.
That makes a lot of sense. Focus on the framework's predictions, not just noisy internal signals. So, wrapping this up, what's the big picture takeaway for you listening? It really feels like this ScaleRL recipe combined with the predictive sigmoidal framework has dragged RL training out of the realm of intuition and guesswork and brought it much closer to the kind of scientific rigor and predictability we've had in pre-training for a while now. It's about turning that expensive gamble into managed risk.
I think that's right. And the key takeaway for me is how cumulative success is in large-scale RL. It's the result of methodically addressing dozens of potential failure points. These individual components, the FP32 fix, the zero variance filtering, the CISPO loss, they might seem like small details in isolation. Some mainly boost efficiency, others nudge the asymptote, but together, their combined effect is what creates the robustness needed to reliably climb towards and actually hit those high-performance ceilings without the whole process falling over. It's about systematically eliminating sources of instability.
A really holistic approach. Okay, that brings us to our final provocative thought for you to mull over. This study gave us a way to predict RL performance based on RL compute. The obvious next frontier, it seems, is to create unified scaling laws that bridge all the phases. Imagine a master formula, one that predicts final model capability based on not just RL compute, but also pre-training compute, model size, maybe even the amount and quality of RL training data. The ultimate question then becomes, if you have a fixed total compute budget for an entire project, how do you optimally allocate it across pre-training, model scale, and RL training to get the absolute best final result? What's that perfect combination? That's the multi-axis optimization challenge on the horizon.